It cost $19.6 billion to construct, consumed 12.3 million cubic meters of concrete, and currently restrains a 29 billion cubic meter reservoir of raw kinetic potential. The Itaipu Dam is not merely a barrier across the Paraná River. It is a macroscopic energy extraction machine, designed to tame one of the most violent hydrological forces on the South American continent. The engineering challenge here is absolute. How do you construct a 7.9-kilometer-long, 196-meter-high fortress capable of withstanding continuous hydrostatic pressure without suffering catastrophic structural failure? Spanning the border between Brazil and Paraguay, the Itaipu Dam functions as a base-load hydroelectric generation complex. Its primary objective is the continuous, unyielding conversion of gravitational potential energy into grid-scale electrical power. The entire system is systematically divided into three primary functional zones: the main concrete gravity structure, the hydraulic penstock intake system, and the central generation powerhouse. Building this structure required diverting the seventh-largest river in the world, excavating 50 million tons of solid basalt rock, and establishing a closed-loop industrial supply chain that operated relentlessly for over a decade. The central heart of the Itaipu facility is its main dam structure, engineered utilizing a specialized hollow gravity design. This is precisely where the extreme physical limits of civil engineering are tested and calculated. A solid concrete dam of this immense scale would not only be economically unviable but structurally compromised due to severe thermal expansion and uneven internal stress distribution during the curing process. Instead, the structural engineers opted for a hollow gravity architecture. The structure relies fundamentally on its immense mass to resist the horizontal thrust of the impounded water, while the internal cavities reduce the total concrete volume and optimize the dissipation of mechanical stress. The geometry of these hollow chambers is precisely calculated to transfer the immense hydrostatic load downward into the bedrock foundation. We are analyzing a continuous force equivalent to the weight of thousands of skyscrapers pressing uniformly against the upstream face of the concrete wall. This requires an absolute understanding of complex load paths, stress vectors, and material deformation under continuous static pressure. The structural integrity of the main dam relies entirely on the precise alignment of the monolithic concrete blocks and the controlled calculated distribution of kinetic forces into the geological foundation. To safely extract the hydrokinetic energy, the dam utilizes 20 massive external steel penstocks, prominently mounted on the downstream face. These are not simple water pipes. They are high-pressure hydraulic conduits, each measuring exactly 10.5 meters in diameter. Every single tube is constructed from highly durable, specialized steel alloys specifically formulated to withstand extreme internal pressure, intense vibrational stress, and potential material fatigue. Through each of these 20 conduits, 700 cubic meters of water equivalent to the volumetric capacity of a large residential building plummets every single second. The water drops a vertical distance of 118 meters, accelerating rapidly under the force of gravity. The friction, the hydrodynamic turbulence, and the shear kinetic force generated inside these steel cylinders push the absolute boundaries of metallurgical science. The steel plates used to fabricate these penstocks had to be precision rolled and welded on site using automated submerged arc welding techniques. Every single weld seam is a critical failure point. A structural breach here under full hydrostatic load would result in an explosive release of pressurized water, instantly destroying the lower powerhouse infrastructure. At the base of these massive hydraulic conduits lies the powerhouse, a heavy industrial environment containing 20 colossal Francis turbines. This is the exact location where the mechanical energy conversion occurs. The high-velocity water exits the penstocks and strikes the engineered curvature of the turbine blades, forcing the massive 1,760-ton rotors to spin at a constant, precisely controlled speed of 92.3 revolutions per minute. The manufacturing of these rotors required heavy-duty industrial casting, utilizing specialized steel alloys resistant to cavitation and continuous mechanical erosion. The installation of these components demanded precision, machining on a cure-thacked megalithic scale. The mechanical clearance between the spinning rotor and the stationary 16-meter diameter stator involves ultra-tight engineering tolerances measured in fractions of a millimeter. A physical deviation of just a few millimeters at these rotational speeds under such immense torsional stress would induce severe mechanical friction, destructive harmonic vibration, and ultimate system failure. Each of these 20 generation units is rated at a maximum output of 700 megawatts, and they must operate in absolute synchronization to maintain the frequency and voltage stability of the electrical grid. The precise aerodynamic machining of the turbine blades ensures optimal hydrodynamic efficiency, flawlessly converting the chaotic linear flow of the water into controlled rotational torque. The sheer scale of the internal components requires an operational logistics network just to maintain the machinery. Overhead gantry cranes, capable of lifting over 1,000 tons, travel along the length of the powerhouse to extract the rotors for scheduled maintenance. The foundation supporting these turbines must absorb the constant, heavy-frequency vibrations generated by the spinning mass and the rushing water. The entire powerhouse acts as a massive anchor block, further stabilizing the dam structure against the horizontal forces of the river. Every single parameter within this complex, from the flow rate of the penstocks to the rotational velocity of the generators, is continuously monitored by a centralized automated control system. Sensors embedded deep within the concrete and along the steel casings measure stress, temperature fluctuations, and structural displacement in real time. Itaipu operates not just as a dam, but as a finely tuned, hyperscale mechanical apparatus, where the raw brute force of nature is systematically channeled, controlled and converted through applied physics and uncompromising engineering precision. The construction sequence of the Itaipu Dam required a brutal, systematic alteration of the local geology. Before the first cubic meter of concrete could be poured, the Paraná River had to be physically diverted from its natural riverbed. This necessitated the excavation of a massive diversion channel, measuring exactly 2 kilometers in length, 150 meters in width, and 90 meters in depth. To achieve this, construction crews utilized heavy-duty drilling equipment and industrial explosives to fracture and remove 50 million tons of solid basalt rock. This was not merely an excavation. It was a large-scale, controlled geological reconfiguration, executed with strict adherence to seismic limits and material extraction protocols. Once the river was successfully routed through the artificial channel via the construction of temporary cofferdams, the dry riverbed was exposed, allowing the primary foundation work to commence. However, the most critical engineering bottleneck during the construction phase was not the excavation, but the extreme thermodynamics of the concrete itself. Pouring 12.3 million cubic meters of concrete presents a severe physical limit regarding thermal expansion. The chemical hydration process of cement is highly exothermic. If a concrete block of this massive volume were poured conventionally, the internal core temperature would spike dramatically, causing uneven thermal expansion. As the exterior cooled and contracted faster than the hyperheated core, the entire monolithic structure would inevitably suffer from catastrophic microfracturing and deep structural cracking, long before the reservoir was even filled. To mitigate this thermodynamic crisis, the structural engineers implemented a radical industrial cooling solution. They constructed specialized, high-capacity refrigeration plants directly on the construction site. These industrial chillers were designed to produce thousands of tons of ice flakes every single day. Instead of using standard liquid water, the concrete aggregate was mixed directly with this crushed ice. This forced the initial temperature of the concrete mix to drop, effectively controlling the peak temperature of the curing process to remain strictly below 7 degrees Celsius. High-speed aerial cableways and specialized conveyor networks transported the chilled concrete buckets directly to the pouring zones, operating with a cycle time measured in seconds to prevent premature thermal loss. This continuous, closed-loop thermal regulation ensured that the massive concrete blocks cured at a uniform, synchronized rate, guaranteeing the structural integrity of the dam against the future hydrostatic load. Beyond the raw material handling, the structural reliability of the Itaipu Dam was subjected to rigorous, uncompromising quality control protocols. The high-pressure hydraulic penstocks and the internal rebar framework required absolute flawlessness. To ensure this, engineering teams utilized advanced non-destructive testing methodologies. Every single critical weld seam on the 10.5-meter diameter steel penstocks underwent exhaustive ultrasonic scanning and X-ray radiography. These deep penetrating sensors were deployed to detect any microscopic air voids, slag inclusions, or internal stress fractures within the steel matrix. A single micro-crack, subjected to the constant vibrational stress and extreme internal pressure of 700 cubic meters of water per second, would propagate rapidly, leading to explosive material failure. The inspection parameters demanded zero tolerance for structural defects. Equally critical to the dam's survival is the spillway system, designed for extreme kinetic energy dissipation. During periods of maximum hydrological flow, the reservoir cannot store the excess volume. The spillway must safely discharge this water without allowing the sheer hydrodynamic force to erode the dam's foundation. The Itaipu spillway was engineered and stress-tested to handle a maximum discharge capacity of 62,200 cubic meters per second. This is a volumetric flow rate approximately 40 times greater than the average flow of the nearby Iguazu Falls. As the water accelerates down the concrete chutes, it reaches extreme velocities, generating massive kinetic energy. The spillway utilizes an aerated ski jump design structure at the bottom, which intentionally launches the water into the air. This aerial trajectory dissipates the kinetic energy through atmospheric friction and turbulence before the water crashes harmlessly into the plunge pool below. If this energy were not systematically mitigated, the hydrodynamic scar would literally excavate the bedrock foundation, undermining the entire $19.6 billion structure. Today, the Itaipu Dam stands not merely as a barrier of concrete and steel, but as the primary kinetic engine driving the macroeconomic infrastructure of two nations. The synchronous generators, coupled directly to the turbine shafts, maintain a constant output, requiring dual-frequency transmission infrastructure to interface with both the Paraguayan and Brazilian national grids. By continuously converting the flow of the Parana River into base-load electricity, this megamachine generates over 90 terawatt-hours of power annually. It single-handedly supplies approximately 90% of the total electrical grid demand for Paraguay and roughly 15% of the massive industrial and residential consumption of Brazil. The transmission lines radiating from the powerhouse form the critical vascular system of the regional economy, stabilizing the power grid through relentless, automated, and synchronized operation. The Itaipu Dam is the ultimate testament to the capability of modern engineering to conquer physical boundaries. It proves that with calculated thermodynamic control, megalithic mechanical assembly, and strict structural testing, humanity can harness the most formidable geological and hydrological forces on the planet. This facility redefined the global standards for hollow gravity dam construction and extreme hydroelectric engineering. If you are fascinated by the complex logistics, the heavy machinery, and the uncompromising science behind the world's greatest megaprojects, make sure to subscribe to the channel for more deep dive engineering analysis.